Okay, so I think let us start. It's time. So in the last lecture, we started talking about flow-based models, right? We started talking about flow-based models, and in flow-based models, we kind of discussed the fundamental aspect of flow-based model, and then we talked about two variants: one where the volume was preserved, the other where the volume was not preserved, right? One that is the affine coupling layer where the volume was not preserved, and the one before that is the one where the volume was preserved. And then we also talked about how to train the model in a broader sense. The objective for today is simple. We will complete our discussion on flow based model. Okay, and completing discussion on flow based model means um, we'll talk about how to implement it, uh, let's say for an image or for a vector. We'll talk only about vector, but the same thing can be applied for image, right? Uh, we will talk about some variants of flow-based models. Flow-based models is a family of generative model. It's not one model. So we'll talk about some variants of that of it as well. But before that, let us do two things. One thing I forgot to mention last time, which is why is it called normalizing flow? So Rakesh was asking me after the class, and that is the time I remember. Not you? Okay, someone was asking me. Anyways, so someone was asking me about the uh, that why is it called normalizing flow? Why normalizing and why flow, right? Which I forgot to mention last time actually, to be very honest. So let us start with that. Let us recap what we did last time and then we'll proceed, right? So to start with, we call it normalizing flow because uh, first we use the term normalizing because the distribution we get is normalized. We do not get unnormalized distribution. What the distributions we get is normalized, and hence the name normalizing flow, because the distribution flows through different transformations to finally learn the target distribution. So it is like that it is flowing through different small transformations. Let's say transformations of the affine coupling multiple times. So that's why we call it flow. So it's the distribution, the probability mass that is flowing uh, through the transformations that we are doing. And that is why it is called flow normalizing, because the distribution we get at each step is normalized. So hence the name normalizing flow. Later we will talk about, towards the end of this course, about flow matching. And there flow will have something to do with velocity, right? But that will come later. The distribution you get is normalized at every step. You do not get unnormalized distribution. It's not prior times likelihood. It is prior times likelihood by evidence. Yes. Yes. Not true. The target is to learn the distribution and sample from it. There might be some distribution where you are able to sample from it, but you are not learning the distribution explicitly. Example in point VAE. VAE, you do not learn the distribution explicitly. You are able to sample from it. You don't know probability of X. But no, that distribution is normalized. If you integrate it, you will get 1. Yes, but there are also unnormalized distribution. Any distribution, Gaussian, ignore the constant part, exponential of minus half x minus mu by sigma whole square. That's an unnormalized Gaussian distribution. So that's what is called unnormalized distribution. Whereas if you take 1 by sigma root 2 pi, that's the normalized distribution. So what you are getting is normalized. Okay. Um, it is not normalized because the distribution is normal, because the distribution need not be normal. It can be uniform also. So then will I change the name? No, I will not. So normalizing because the distribution you are getting is normalized. Flow because it is flowing through different transformation to give you the target distribution. Okay, so that is it. So now to quickly recap, we were talking about flow based models last time, and the idea of flow based models is based on two simple principles. It is based on two principles. What are the two principles? The first principle is that transformation of variable, the transformation of distribution. So that is the first principle which is governing this model. Transformation of random variable, right? What is the second one? Some mappings that are invertible, invertible functions, invertible functions. There is also a third one. What is the third one? Computationally tractable, which means obviously computationally tractable. These are the three guiding principles that we talked about last time. I mean, these are the three conditions, three guiding principle, whatever you call it. These are the foundation of flow-based model. Transformation, which is fxx is equal to fzz dx by dz, or dou x by dou z, modulus of that or determinant of that. If you take, so basically the Jacobian. So that is the first one, transformation of random variable. Now to do that transformation of random variable, you need a mapping which is invertible. We saw that last time, because you need x in terms of z and also z in terms of x. So that's what invertible means. Thirdly, obviously all this computation has to be done in a computationally tractable manner. If I cannot compute the Jacobian, if I cannot compute the determinant, if I cannot compute the invertible thing, then it does not work. Okay. Now last time we talked about two models. What were the two models? So we talked about two models. The first one was x1 prime is equal to x1 and x2 prime is equal to x2 plus m theta of x1, right? So this is the forward pass that we talked about. The inverse or the reverse pass, whatever you call it, is x1 is equal to x1 dash. One second. And x1 is equal to x1 dash and x2 is equal to x2 dash minus m theta x1 dash, right? So this is the volume preserving version. This has a name. This is known as NICE, NICE. So this is the NICE algorithm. Okay, and there is a, I mean, when it was originally proposed, this was the one that was used first, and later the other one that I talked about came into picture. So this is known as NICE. Okay, but what is the limitation of this? The volume is preserved, which means it is not enough, it's not expressive enough. So the other one came into picture, which is the almost same, slight difference, right? X1 dash is equal to x1, x2 dash is equal to exponential of s theta x1 element wise multiplication with x2 plus t theta, which is m theta x1. And I can write the inverse mapping as well. I am not writing it, but if I want, I can write the reverse or the inverse mapping as well. So this also has a name. I did not mention the name last time. It is known as real NVP. What is NVP? Non-volume preserving. It does not preserve the volume, right? So NVP is non-volume preserving. It is known as real NVP. Okay. NVP stands for non-volume preserving, and we know that the determinant is not 1 in this case. Can someone close that door, please? Thank you. So we call it real NVP. So that is non-volume preserving NVP. Yeah. What is the weights and biases of the neural network? Because you always keep in mind S and T and M. M in the first expression and S and T in the second expression. These are neural networks. And this can be like multi-layered neural network kind of thing. It need not be a single layer. And this is a transformation that you will not do once. You will do it multiple number of times. It's not something you will do only once, right? In fact, if you do it only once, your transformation will not be expressive enough. The whole idea is you do it multiple times, you change x1 and x2 and all of those things. Otherwise, this is not expressive enough. And we saw that when we draw that. I mean, you saw that one. If I do it only once, one direction does not change. You need to do it again. We saw that last time. Yeah. Yes. Yes. No, not shared. Not shared. Not shared. So, like the question is that if I have multiple affine coupling layers, each one will have S theta and T theta. So, are those shared? Are those theta same? No, they are not same. Each affine coupling layer will have its own theta. So, when I am writing theta, it is kind of like union of the theta 1 and theta 2 and theta 3 and theta 4. So, it's a set that is union of all of those things. I am not mentioning it, but theta is in a broad sense, right? Otherwise, if that could be possible, then the number of parameters will be very less, which is unfortunately not the case. Okay. So, anyways, this is nothing new. This is what we have already discussed. But one thing we did not discuss is planar flow, right? So planar flow is technically, I will not call it a invertible neural network, but planar flow where everything started. There was one paper before that, but planar flow actually used. So remember, what is the motivation of this normalizing flow? That is the motivation of any generative model. What is the motivation of this? Likelihood, right? The likelihood is not tractable in where? VAE. So in variational autoencoder, the likelihood is not tractable. That is the motivation for this. But that jump from VAE to normalizing flow was not a one-step jump. In between, there was something known as planar flow and radial flow in a paper that came out, where they were still using variational inference, but bringing in these concepts of flow, of distribution and all of those things. So this planar flow is a model where you cannot actually invert it. The model is invertible, but you cannot invert it analytically. So you can invert it by using some Newton's iterations and all of those things. You get a one-on-one mapping in the inversion as well. But otherwise, you cannot find it analytically. And because you cannot find it analytically, it's the third condition is compromised, which is computational tractability. So that condition is compromised. So they don't do that. They don't go the opposite route to find out the likelihood. They use variational inference, but the concept of flow is also embedded in that. So they call it variational inference flow or something like that. I forgot the name of the paper. I think it is a paper in 2014, 15, I think. Not really, because what I said was that is the in-between paper. So VAE was there. Then this thing came, which was kind of trying to address the likelihood part. But then they realized even that is not. So then they go to normalizing flow. But having said that, is there an advantage? There can be advantage for some problem that might work better. Right? It is not that it is guaranteed it will always work better. The reason is that you get the exact likelihood, but that remains a non-convex optimization problem. So you will still get stuck at the local optima. if you'll get stuck at the local optima, it is possible that the elbow becomes easier to optimize as opposed to this. So in that sense, computationally, numerically, you might get some advantage. Uh, Number of parameters might be more here in normalizing flow than VAE in many cases, but otherwise, this one is generally better. Okay, so what I was talking about is planar flow, right? So there is this idea of planar flow which started, which is basically, the idea is basically that if you want to find out, let's say, h of z, this is equal to z plus b, okay, not h, let's write it f, okay, f, because h means hidden, right? So b, then sigma w transpose z plus b. So this is yes, this is the planar flow model, which is kind of additive. And the learnable parameters are w, b, and b. W, okay, there are two b's now. I cannot have two b's. Let's use something, right? B prime. Okay. So the learnable or the trainable parameters are w, b, and b prime. All of these are free parameters that you optimize for. And sigma is a monotonically increasing or activation function. Monotonically increasing is very important here because of it is monotonically increasing, you get a one-on-one mapping in the reverse sense. Otherwise, you might not get. Okay. So this is basically what is planar flow is. But this is not unconditionally invertible. And this is not unconditionally invertible because you need to compute the Jacobian and look at the determinant of that. Right? If you compute the Jacobian, what will you get? Dou f z by dou z, let's say, right? Dou f z by dou z, which is equal to I, right? Plus b prime sigma dash w transpose z plus b multiplied by w transpose. That's what you will get, right? And now if you want to find the invert of this, you can find the inversion of this by using something that is known as matrix determinant lemma. So there is something known as the matrix determinant lemma, which basically gives you that if you have a function like a plus u v transpose whole inverse, no, a plus u v transpose, you want to find the determinant of that is equal to determinant of a multiplied by 1 plus determinant of u and v transpose, so something like that. Okay. So you can use the matrix determinant lemma, add it to the homework, the derivation of that. Okay. So there is something known as the matrix determinant lemma, and you can use that to find the inversion of that. So finding the inversion is not really a problem, but the inversion, after doing the inversion, you will get an expression, and you need to enforce that that expression is not equal to 0. And only if it is not, when it is not equal to 0, this thing will remain invertible. So this is not unconditionally invertible. For making it unconditionally invertible, you need to do some trick. You need to enforce some constraint on w and b prime, so that the determinant never becomes 0. The matrix never is non-singular, it is never singular. Okay. And also the inversion, if you have to find out the inverse mapping, that also you cannot find it out quite obviously. For sigma is non-linear, you cannot find it out analytically. You need to find it out by doing the Newton's iteration or something, some iterative method, and that is needed to find out the inversion of that. Okay. Yeah. So the points that I said, I'm not going to derive these things because this is not that useful, to be very honest. No one uses it now, uses it nowadays because it is neither VAE nor flow, somewhere in between, and people do not prefer that. But it is important to know about it from a historical perspective, because you should know that how it went from variational to flow. So in that perspective, I'm just introducing this, but I will not go into the details, right? Anyways, so this is your what I said was this is not unconditionally invertible. Okay, this is not unconditionally invertible. The other thing I said was determinant is computed using matrix determinant lemma, which is something like, let me write it down, you should verify this. Okay, A plus U V transpose, you want to find the determinant of this. Okay, this is equal to determinant of A multiplied by 1 plus U A inverse V transpose, something like this. Can you verify? It is written there. But this is the one, right? I think this is the one. You can use this to find out the determinant of the Jacobian. And it will be easy because what will be A in this case? Can you tell me? Identity, right? A will be identity. So A inverse will be identity. And then U will be, yeah, some portion of it will be U, which is sigma dash times whatever it is. And V will be the W transpose part. So there will be 3 terms, but you can take the first term as U and the product of the next two as V. And that will give you U V transpose, that form, and then you do that. Okay. So you can use it to find it out, and this is kind of, uh, the advantage of this lemma is that it is very easy to compute when you write your computer code. So that's why it is important. Okay. But U A transpose. Okay, it's opposite, right? Okay. Okay. Yeah. Okay. Yeah. So no, they are just two vectors. Yes. You will do multiple times for each layer. You will do this, right? Something like this. Anyways, you verify this. Please verify. I'm writing it. Don't take it. Verify it. Okay. So this is the idea of flow matching. This matrix determinant lemma is very common in probabilistic machine learning, the classical one, right? But here it is not that used that much. But in some cases where you need determinant, this becomes quite handy. But again, this is just for the introduction part. This is generally not that useful nowadays. Okay. Okay. So now, so basically, variational autoencoder. Then this one, planar flow and radial flow. This is planar. You can have a radial also. Then comes the real NVP and NICE and all of those things. So that is the timeline we are looking at. Timeline is VAE, then this flow, planar flow, then NICE, and then real NVP. So this is kind of the timeline we are looking at. Okay. So to set that timeline, I kind of introduce it, but I'm not going to details. If you're interested, you let me know. I can share this paper with you. Okay. Good question. So you can show that if you decompose it into orthogonal component and planar component, it actually does the planar. Plane is where the transformation happens. The orthogonal remains the same. So in that sense, you can show that one. So, and so that's why you can decompose it into, let's say, z parallel and z perpendicular in that term. So in that sense. Also, I mean, if you go to the eigenvalue space, and that is where things get interesting. If you compute the eigenvalue of this matrix, it is only one eigenvalue will get changed. Everything else will be identity. So one eigenvalue will get deformed or changed because of this transformation. So those are the mathematical analysis which are very nice, actually, to be very honest. But hmm? Not stretching exactly. In the planar, you can have different types of determination, right? Deformation. So it might look like a stretching in one direction because eigenvalue means you are actually rotating it in the principal direction, and then one of the direction is getting stretched. But when you are in that plane, you will see multiple things, but everything will be planar. Okay, so that is the thing. So the flow, the change of distribution is happening on a plane. So that's why we call it planar. In radial, this is not radial. In radial, it will happen in the along the radial direction, cylindrical coordinate kind of thing you can imagine. Okay. Okay, so we'll not talk about planar. So next, I'll talk. Yeah, go ahead. Which is the g theta? No, no, no. So z is the starting. So that is the latent variable. And fz is the, let's say, z1. And you will do it multiple times. So you get z0, z1, z2, z3, zn. Zn is your x. So this is one layer. Oh, because in invertible neural network, you need to go from z not to zn and zn to z. So each layer being invertible means that the whole thing is invertible. So to go from x to z or z to x to z is the invertible one, right? It has to be that from x to hk, hk to hk minus 1, hk minus, each of this is invertible. Only then the total thing is invertible. Okay. Uh, okay. By the way, when I say the determinant has to be, non-zero, right? And I said that you can find out the condition. That condition is not unique. That condition depends on what? Sigma. If I take tan hyperbolic, I will get a different condition. If I take something else, that condition might not exist at all. But, so in that sense, so keep that in mind. When I'm saying that, to make the determinant non-zero, to make the matrix non-singular, I will have to put some additional constraint. That constraint is a function of what sigma you are selecting. Obviously, because your gradient will be function of sigma. So it's quite obvious, but I thought I should mention it. Okay. Okay, I'll talk about other variants of normalizing flow as well. Maybe let me talk about other variants first, and then I'll end the discussion with how to handle when you have a single vector, right? So let me end with that. So let me continue with other types of normalizing flow. Okay, okay. So we have already studied this thing, right? Autoregressive generative model. Can you remind me what is autoregressive generative model? What do we do here? We, as a, the product law, right? The decomposition. So here what we do is that we do it pixel wise. P of x is equal to P of x1, P of xj given x less than j. 1 to, I don't know, k maybe. Okay, not 1, 2 to k, 2 to k, right? We know this, right? This is the first generative model that we studied in this course. Correct. Now, not all autoregressive model, I should write continuous autoregressive model. Okay. So what I'm talking about now is not the, let's say, the categorical autoregressive model. No. I'm only talking about the continuous variant of autoregressive model, which is the where the prior or the P of x1 comes from Gaussian, right? So the question I want to ask is that can we imagine autoregressive generative model as a type of flow-based model? Can we imagine autoregressive generative model as a type of flow-based model? Think about it. The question is clear? Hmm? That's what. Think about it. Can you think? The answer is yes, but can you think? Someone says sort of. P of x1 as a Gaussian, not prior. Correct. Correct. Ancestral sample. It's like a flow, right? So in that sense, what he just said, right? I'll write it down also. You are sampling from what? A Gaussian? You're conditioning on that Gaussian to sample from the next one, and for that you are passing it through a neural network to find out the mean and covariance, and then sampling from the next conditional Gaussian, and this continues. Any question? No. In this case or in this case? Correct. So in this case, when I'm comparing it, here it is just the 1 pixel. So I'm taking 1 pixel, its distribution is Gaussian, and conditioned on I'm sampling the next one. Ultimately, I'll get all the pixels. So it is like flowing through simple distributions to somehow learn the actual distribution. Making sense? I'll write it down anyways, but they are conditionally independent in that sense. Actually, they are not independent, conditionally independent. For P of x2 given x1 and x3 given x2 and comma x1, I mean x3 is dependent on x2 and x1, right? Sampling is involved, obviously. Sampling is involved even in flow. We do it like that. But when you will actually sample it, what will you do? You will sample from Z, and then on those samples you will pass it, right? So that transformation that you do, it happens on the sample level. So even in flow, sample is involved. But you were not asking the actual question. But I was expecting one question. Yeah, go ahead. This one is obviously guaranteeing one-to-one mapping right now, because but you are in the right direction. But let me answer that first. The question that I want you people to ask is where you are approaching, but obviously from x1 to xk, that is one-to-one, right? So is that what you were asking, or you were asking the reverse one? Correct. So that is now the correct question. One option is obviously it is flow, because you can understand that you are transforming, I mean, you are taking small distribution, doing some product over them to arrive at the final distribution. And the Jacobian of that, if you check, it will be diagonal and lower triangular, because x1 is independent, x2 is only dependent on x1, x3 is dependent on x2 and x1. Because of that structure, you will get a lower triangular. So the Jacobian part is sorted. But that is the correct question. But that is not the only criteria. The mapping also needs to be invertible. So is it invertible? Can we somehow, if I know the final sample, can I find the previous ones? Because if I cannot, then we are not in the business of flow-based model, right? So let us see. Let us first write down the sampling and then let us see if we can. Okay. So in autoregressive model, and I'm only talking about sampling right now, okay. What we do is, what is step 1? Step 1 is to sample x1 from some Gaussian with some mean and some covariance, right? Or some variance, because it's a single pixel, so not covariance, variance. That's what you do. In autoregressive, you first sample x1 from P of x1, which is Gaussian. We'll not do that. We'll do the reparameterization trick. So I will sample Z from a Gaussian with standard Gaussian, basically, zero mean and unit variance. So step 1, let's say I sample Z from a Gaussian 0, 1. Okay. Step 2, I find out x1 as mu1 plus sigma 1 times Z, right? So that is my now sample. Instead of drawing it in one step, I am doing it in 2 steps. Third step, I find out mu2 comma s2 by passing it through some neural network with and what will I pass? I will pass x1, right? Correct? Step 4, I will find out x2 as mu2 plus exponential of s2 times z, right? Exponential I am doing so that it is non-negative, obviously, right? Clear? And this I can continue? Yes, very good. You can sample again. I'm using the same sample, but you should sample again. I'm not showing it, but you should sample again, right? Okay. Because right now sampling is not the point. I want to relate it with the invertible one, so that's why I'm not doing that. Okay. Correct? This is the, and then you can continue like that. And you can continue. I mean, now, if you say these 2 steps, right? Or maybe only this step. This is like drawing Z from Gaussian of 0 and 1, which is exactly like the first step of normalizing flow during inference. You draw from Gaussian. And then, again, only the forward pass I am doing. I will come to the reverse pass soon. Then, if you go from this step to this step, this is like one layer of transformation, right? One transformation happened. Now you have x2 and x1 both, and you continue like that multiple number of times. So you can have a one-on-one comparison. It is not exactly same, obviously, because there the dimension was always same. Here the dimension is increasing one by one. So all those differences are there, but you can find some similarity. They are not same, but there is some similarity, right? However, the question, as correctly asked, is that is it invertible? It is invertible if you see, uh, if I know x2, I can find out z. It's the same affine coupling, same thing. Given you know mu2 and s2, and mu2 and s2 are actually parameterized by theta. So if I somehow know mu2 and s2, then this is exactly same as the affine coupling layer. And because affine coupling is invertible, this is invertible. The condition, however, is that mu and s should be known, right? Making sense? Any question? No question, right? So if mu and s are known, this is invertible. The question, however, is that how is mu and s known? Now, let me ask one more question. In normalizing flow, whatever we discussed last time, when the invertibility condition is needed, during training or during sampling? When is it that the or the reverse mapping is needed in normalizing flow? Training, right? So that means this invertibility condition that we want even for this should be accessible to us during training. As long as it is invertible during training, we are fine. We don't need the invertibility condition during sampling. Correct? Yes, real NVP and NICE is invertible even during sampling. But we don't really use that. That's an added advantage we have. But we need invertibility only during training. Everyone is following that? Any question? Okay, so let us write that. Note that invertibility is needed during, I should write only during training, but I'm writing during training. You can add the only term if you want. I mean, that's the correct term actually. It is needed only during training, right? Now, S and mu, these are function of what? Theta and x. What is x? Training sample. So is x not available to me? X is available to me. Theta during training, for a given iteration, I will have some theta, which will get updated, but theta will be known to me. Correct? So x is known to me because it is training data. Correct? Theta is for a given epoch or given iteration is known to me because it's for that epoch I have some guess for theta. So does it not mean that in terms of that theta that is valid for that iteration or epoch, I can always find out mu and s? Right? The problem, however, will be that I cannot find it out together because of the conditioning thing that you are seeing. Because it is x2 given x1, x3 given x2. So because of that conditioning change that you see, I might not be able to find it together, but I will be able to find it out. I'll repeat once more. We need invertibility condition only during training. And this expression, what I'm seeing on the screen, is invertible as long as I know mu and s. Mu and s are function of x and theta. It's a nonlinear function, but of x and theta. X is known to us during training. Theta for a given iteration is known for that iteration. It will get changed in the next time, but it is known for that epoch or iteration, right? Which means I can find out mu and s anytime I want. And because I can find out mu and s, if I know x, I can go to z. Correct? Clear? So this becomes, I mean, I can train it in the same manner as real NVP. the same training thing that we talked about last time, we can. And I already told you that the Jacobian that you will need, because of this dependent structure, it will be triangular. And so the determinant will be product of that diagonals. Any question? Any nonlinear. Monotonic increasing, obviously. That is always the. Yes, yes. Any activation function you can use. Do you need to invert the nonlinearity? You don't need to. M theta and S theta was also having, right? Same thing. Yeah. Go ahead. First there, then I'll come to you. Repeat again. Correct. F theta 1 is reducing the dimension. Why is F theta 1 reducing the dimension? It is always same. The input is increasing. And I'm coming to that in a short while. The input is increasing, output is same, right? Mu and S, always. Yeah. I will come to that. Yeah, I'm coming to that. Okay. Yes, obviously. X1 to Xn and each one is having k pixels. Yeah. Again, you're confusing here. Here, when I'm writing x1, x2, these are not data. These are pixels. So when you say n is the number of data, you mean xk, I guess. Yeah, xk, then it's fine. Yeah. Correct. For all sample, actually. Correct. F theta 1, F theta 2, F theta and all. Uh, it has to be trained separately. That's what I was saying, right? Because each of the network is having a different parameter, right? Theta 1 I wrote. Z is anyways different, right? Huh. No, you will sample at different point. You will sample. I just wrote it just for understanding, right? Yeah, no. So that I think that is the same thing. I think he asked, right? So you will not. Any other question? Otherwise, no, it is not sample wise. It is pixel wise. So each pixel will have a neural network, not each sample. That for the pixel, all the samples will pass through the same network, right? Same as autoregressive, what we are doing. Correct. While training, you use what loss? Likelihood. Likelihood, right? Likelihood is summation over or product over all the data. Is it not? Likelihood is probability of d given theta. Because the data are IIDs, it is equal to product of I equal to 1 to n probability of xi given theta. For each of this probability of xi given theta, you will get the likelihood, right? Again, you are confusing. You are confusing between pixels and samples. Pixels are not samples. You go back to the autoregressive. I said each image has k pixels. Those pixels are not independent of each other. Then cannot be. Then it will be random noise. But you have n such data, each data having k pixels. Those data are IIDs. The likelihood is over the data, not over the pixels. Right? So don't confuse between pixels and data. Obviously, that's obvious. There is nothing new in that. Scalability issue is there in even normalizing flow. Diffusion is much more better in that case, but yeah, sorry. mu1 and sigma1 are not learnable parameter. The first one, right? Here I am assuming that you know. I mean, obviously they can be learnable also. Here I'm starting with the second one, obviously, to draw that. But yeah, generally they can be learnable. Okay. But if they are learnable, that's fine because they are constant. I mean, there's, but they don't have f theta. Here I am writing mu1 and if they can, I mean, they are not f theta. They are directly learnable because they are not conditioned on anything. Because mu1 and s1 or sigma1 are related to x1, and I am starting with the expression that p of x1. That means x1 is independent of everything else. So because of that, they have to be learned directly. They are not function of any x. As in weights and biases, they are directly like a weights and bias. Then there is no network there. So when you optimize, you have theta 1, theta 2, theta 3, theta 4, theta 5 like that, comma s, comma sigma, or comma m, comma sigma, whatever you call it. Yeah, there was one more question, right? You can do that actually. Yeah, that's parameter styling, right? Yeah, you can do that. But we will generally this is not used with the usual NAID. NAID is generally not used with this, and that is the next thing I'm coming. So that's why I gave that statement that you will like to learn everything together. So with this, generally what is used is MAID, mask autoencoder density estimation. So MAID is what is used here, not NAID. Okay. So note that invertibility is needed only during training. Now at this time, x is known, theta for an epoch is constant. So mu and s can be determined, which finally means it's invertible. Okay, which means it's invertible. Okay. Now I talked about MAID. Now MAID, I mentioned it. It is there in the practical, but we never did it actually. So let me write down, not the exact MAID I will not do because that is for you to do, but let us in that MAID fashion how this will be done. Let us do that. Okay. That in MAID fashion, how will you do this? So the architecture will look something like this: x1, x2, some xi, xk. What is x1? The first pixel. x2, the second pixel. xi, the ith pixel. xk, the last pixel. Right? Because this is a very common confusion I also used to have between pixel and data. So that's why I'm repeating. Okay. So this is the thing. So now, suppose I wrote I. So I want to find out mu I and Si. I mean, ideally I should draw two circles, but I'm drawing one because they will be found out together, right? Mu I and Si will be function of what? Xi minus 1, this one, something like this, right? Correct. And then in the bottom you will have right, correct. And your Zi you will find out as function of you can, right? So now if you, so this is actually the mask encoder where what you do is that for each pixel you first have a numbering, and based on that numbering only the pixels that are having number less than that pixel value have a active edge, and whatever pixel has number equal to or greater than that value will have, it will mask it with 0. So those edges will, you will remove, like drop out. I mean, it's not drop out, it's called masking, but you can imagine what I'm saying. I'll repeat once more because this is something different. You can see xi is conditioned on x, or xj is conditioned on x less than j. So imagine a pixels, right? x1, x2, x3, x4, x5. So when it is x5, I'm finding out mu5 and s5. Mu5 and s5 is function of what? x1, x2, x3, x4. So that means those edges will be active. Other edges will be equal to 0. They will vanish. So they will be masked. Right? This is the idea of mask encoder. When you mask like that, you just do a forward pass, you get all the mu and s together. So you just create, it's a data structure management, nothing else. It's a data structure and algorithm thing. You just create a mask weight matrix, do the product, you will get all the mu and s in one sweep. You don't need to do it again and again. Once you get mu and s, you just do this invertible operation and you will get z, all the z together. So it will become just a single pass. I'll repeat once more. This expression is telling me that xj is function of everything that is less than j, which means if I'm finding out xj, it should be x1 to xj minus 1. That will be influencing my parameters of this, right? That means those edges should be there. Every other edge should be removed. And if you create masking like that, where some weights you are making 0, that weight 0 means edge is not there, right? When you mask it like that, you just do a multiplication, you will get everything. And that allows you to do the thing in one pass, make it faster, nothing else. You can do it one by one also if you like. I mean, then it's very slow and not useful. So this is the idea of mask autoencoder. And when you use mask autoencoder in this fashion, it is known as mask autoencoder flow, or MAF. So this is known as MAF. I will give you one diagram of mask autoencoder because, or MADE. So in MADE, the network looks like this. You have x1, x2, x3, and then let's say some, and there can be more networks also, and then let's say x1 hat, x2 hat, x3 hat. Let's take it like this, and let's say that probability of x is equal to p of x3 or x2, p of x3 given x2, p of x1 given x2 and x3, something like this, right? That means this x1 hat, see, where is this x3 hat, sorry, x2 hat, this one should not be connected with any edges. X2 hat should be independent. X1 hat should only be connected with, sorry, x3. X3 should be connected with only x2. So let's say something like this. Okay. There can be additional edges. I will draw that, but let's see. And x1 should be connected to x1, x2 and x3. So it should be connected to x3 also. And it can even go through this. So it can be like this. This is one example. This need not be the correct example. There can be other variants also you can come up with. But when you mask like this, where these edges are only active, you see x1 is connected to both x1 and x1 is connected to both x2 and x3. x3 is only connected to x2 and x2 is independent. Autoencoder style, so reconstruction, because autoencoder style is what? You will give x1 and you will get x1 hat, right? In the autoencoder style, so that is x1 only. I am writing hat because ultimately it will not be exact. So x1 hat is x1, x2 hat is x2, x3 hat is x3. But it will not be exact, so I am writing hat because you will not be able to train it perfectly. Correct. So look at the expression on the right. P of x2, that means x2 is not dependent on either x1 or x3. So look at x2 hat, it has no connection going to it. So all the connections that are going to x2 hat has been removed. So it becomes independent. Correct? x3 is dependent on x2. So see, look at the connection that is going to x3, you will see that that will only connect you to, oh I have done it wrong, I can see. There is a mistake, right? This would not be connected. This one is wrong. Right? So now x3 hat is only function of x2 and x1 is function of 2 and 3. And whatever edges you are seeing not there, that are masked, that means that weights are put as 0. Clear? So this is made. This is the mask autoencoder that is given in practical 2. So this is the implementation you have to do. But this implementation, when you apply to this flow based, we call it MAF, mask autoencoding flow or something like that. Autoencoding or autoencoder, I don't know, but yeah. So this is known as, not this one, where is that? This one. MAF. Okay. Next slide. Mhm. X2 is function of what? Mu and mu2 and s2. Mu2 and s2 are function of what? So x2 is condition on. That's your answer. X1 and x2 both. Yeah. So it is that sense, right? That was a doubt, right? Any question? Relating variable. The yeah, Gaussian mostly. Okay. Mid. Yeah. X3 can go to x1 in multiple way, right? It, yeah, I mean because it can go through multiple transformation also. That is random. H1 is hidden. That has nothing to do with that. You have to go trace back to the original one. Don't look at H1, H2, H3. That I have drawn randomly. It can be changed and there can be other sequence. For programming, you have to come up with some logical sequencing to do that. You cannot make it random like I did. But this random is also correct. Yes, this is actually the dependency only, right? Any question? Anyways, we will implement it in practical too. So that will make things more clear. Okay, one more thing. Map. MAF, right? Training time, it is parallel, right? You can process everything together, you will get mu and s together. The z's you can generate together. So you can get p of z together and that will be matched with Gaussian, let's say, and you can do it, right? What about sampling? How will you sample? Sampling will be exactly like ancestral sampling. It's an autoregressive model at the end of the day, right? It's just a different way of training the model. The model remains autoregressive model. So sampling will be, will first sample x1. Based on that, you will find out mu1 and s1, mu2 and s2, and based on that, you will sample x2. Based on that, you will x1 and x2 will find out mu3 and s3. You will sample x3. You will go the ancestral route. What does it mean? Sampling is slow. So in map, you get a fast sampler, fast training, or faster training, also not the fastest, but somewhat fast training. But the sampling part is slow. Can we do something to make the sampling faster? No. Sharing parameter will not help here, right? Because it has, you have to sample x1 to do go to x2. That's the whole idea of this expression. You can vectorize also will not help because the sampling itself is x1 has to be sampled to get x2. There is no other way that you can sample them together in this form. But one single neural network during sampling, remember you don't training not, I'm talking not training. You don't have any sample. So what will be the input to the neural network? You have not sampled in the previous step. Right? So yes, you can do it. This diagram I have drawn has to be reversed. So here mu was function of what? X. You make mu and s function of z. That means what was parallelized during training, if I reverse that, it will become parallelized during inference. But during training, then it will become slow. So that is also a strategy you should read about it, which is known as IAF, inverse autoencoding flow. This is the forward, so you just call it mask autoencoding flow, MAF. That is known as IAF, which is the inverse autoencoding flow. The idea is exactly the same as this. The only difference is that mu and s are function of z's now, and you find out x as a function of z. So that means you will first sample z, all the z's together. For all the z's, you will find out mu and s, and using that mu and s, you can in one go sample x. Right? So it becomes easy. But during training, then the problem will start because there you have to now do sequential. Because now mu and s are not function of x, they're function of z. So then things will start getting tricky. So this is known as IAF. I'll show you the diagram also. So it should be somewhere here. So this is what I was talking about, right? I just draw this diagram only, the left one. So you have to see alpha I and mu I is like your mu and sigma, whatever you call it, right? They are functions of x. So you sample them, and then you take z also, and you can go to x. Or if you take x, you can go to u. U is z in this case. So see, training and sampling are opposite. Training is the right hand side, sampling is the left hand side. So this is the map. Mask, okay, not auto-regressive, sorry, I was saying auto-encoding. Mask auto-regressive flow, correct? And during training, you can easily understand that for finding out alpha I and mu I, you need x1 to xi minus 1. So it is sequential, right? Any doubt? Any doubt? Loss function is same, nothing will change. Likelihood, probability of x given theta. Loss function will not change. That is the whole idea of going. I mean, why am I doing this? All these things, so that I can use the likelihood. This to diagram. Is it clear? Is it making sense with what I drew earlier? Exactly same, right? This is the mask autoregressive, right? This is what I was saying. So it has changed, right? Because it has changed, now things are tricky. Things are tricky because during this is the sampling, right? This is during sampling. So during sampling, this is fine. You can see you sample all the U's together, For all the u's that you are sampling independently, you find out the alpha I and mu I, and from that alpha and mu I, you find out x all together. So sampling becomes very fast here, but training part will become trickier because for training you have to go from x to u, and that has to be now done sequentially. Okay. Because during training, what will happen? You will give x1, from that x1 you will get u1. Using that u1, you will find out alpha 2 and mu 2. From that alpha 2 and mu 2, you will get x2. Using x1 and x2, from x2, then again, from x2 you will get z2. Now from z2 and z1, you will get alpha 3 and mu 3. So the training now becomes autoregressive. Clear what is happening? But the inference, or not inference, sampling is parallel. We just need the x, that's all. Because you will not get xd until you have samples of ud. Because x1 is the first pixel, right? x2 is the second pixel. xd is the dth pixel. So imagine the MNIST data set. You have 28 cross 28, right? Which is something like what? 784? 784 pixel. So capital D becomes 784. So now you need to sample all the pixels, right? So you cannot do that. So again, the same confusion, right, between data and that. Any question? What is the advantage of MAF? Training is faster. What is the advantage of IAF? Can we do something in between? How? That is exactly what parallel WebNet does. So it uses something known as teacher-student forcing, which is a concept in RNN, right? So here what you do is what is easy to train out of the MAF and IAF? MAF. So teacher will become MAF. So you train the teacher with MAF, and then the student is trained with KL divergence between MAF and IAF. So I'll just focus on this one. Let me convert it into laser, right? So this is the part where the teacher is getting trained, right? And you can see MAF is getting easier, right? Come here. You start with U. U is your Z. You go through IAF. That will give you your X, right? X and log probability, obviously, both. The X you give it to MAF inverse, but the weights are frozen. So this is pre-trained. This is the teacher. That will give you this log. This and this should match. So you minimize the KL divergence between the two. That will give you the parameters of this student. Why do you want the parameter of the student? Because that is fast to sample. If you have to deploy it, then you will just take the students. Once this is trained, you just need the student one. Take and deploy it. It will give very fast sample. That is the idea of this parallel WebNet, which was developed by Google DeepMind, and it was making huge noise when it was developed. They marketed like anything. This is the parallel WebNet, which was developed by Google for speech, I think. Training reduces actually, because if you are not having this teacher, look there, not if you did not have that teacher, right? Then what will happen is that this one you will see with this you are not generating samples. You are generating samples here, but are you training for it? No, right? Because if you remember, IAF dot backward is expensive, right? And MAF, so that is MAF dot forward is expensive. So now look at it. There is no MAF dot forward or IAF dot inverse. No, train the left one first. First you train. No, 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 no. You train this whole model and freeze it. Then you come here and then you only train this one. And because there is no IF dot backward, so you are fine. Okay. And because there is no MAF dot, uh, yeah, so sorry, because there is no IF dot inverse, you are fine. And because there is no MAF dot forward, you are fine. Not parallel. Not parallel. Parallel because there are two things, right? So that's why. Hmm. I mean, you can make it parallel sometime because then what happens is that if you can also switch, right? I'll do it for 5 epoch, then 1 epoch of this. That also you can do, right? So that's yeah. You can do that. That's but I don't think that is needed. But idea is that you avoid likelihood evaluation during the inverse. There is no likelihood during inverse. That's the whole idea. Because likelihood inverse evaluation is expensive for the inverse one. Okay, and again, the last I have given the link from where I've taken screenshot. So this is a blog from where I've taken screenshot. That link is there. Okay, this is not my diagram. This is so okay there. Okay, likelihood, finding out the likelihood or training based on likelihood. Maybe that is the correct terminology. Of the inverse is expensive. So for the inverse, you train it based on KL divergence, and KL divergence where one of the target is coming from the teacher. Okay. More or less, yes. I mean, scalable enough in the sense it can go to very high number of pixels. But are they the most scalable? No, obviously not. If they were the best, then the models that will talk after this, I mean, not GAN, but let's say diffusion and flow matching would have not emerged if they were so good. They have limitations, obviously, and that's why these other models have emerged. Uh, but they can handle large data more or less. You can train, let's say, a model having, I don't know, several thousand pixels easily with this. So that is not a problem. In fact, you have to remember that Google DeepMind developed this, right? They were doing it for speech or something, which is like a very long vector kind of thing. So it works more or less. Okay. Obviously, diffusion is better, and that I don't think needs my justification or why is it better, right? So that is obvious. Yeah. No. Actually, for speech, it is more simple, right? It is actually difficult for image because for image, what is the sequence? What is X1? We talked about it. It can be anything because there is no sequence in an image. What I want, I am using the term pixel because by default, I am thinking about image, but it need not be for image. It need not be pixel. It might be the first data point. Time steps. It will be time steps only. And autoregressive is good for time steps only. I mean, for time. I mean, for time series data, autoregressive is a natural fit. For image, it is actually not a natural fit. It's a forced fit, and that is why you don't see that. Let's say something that generates new images, some vision foundation model, right? In many cases, right? They will probably use some diffusion and all of those things. Whereas GPT, they use autoregressive and transformer. They don't use diffusion. So those kind of models are actually better for images, whereas autoregressive is actually better for speech and language and some forecasting where there is that inherent sense of x1, x2, x3, x4, right? So in that sense. Okay. Did I draw? No. There is one more variant is there, which I mean intentionally did not put here, which is the Gaussianization flow. Okay. Videos has to be combination of two, I would say, because there is space and time both. So in space, probably diffusion; in time, more probably, or frame, probably. What you said, the autoregressive, right? Okay. So there was one more, which is the Gaussianization flow or something like that. There is actually many more, but that is one of the thing that comes to my mind. There, what you do is that you use the CDF and inverse CDF transform to do things. Okay, but I did not put it here. But there is, I have got 5 minutes. I want to talk about how to use it for vector. Right, that I have not done yet. Okay, so now to wrap things up, now when I'm saying how to do it for vector, I'm going back to real NVP. Again, remember the real NVP is perhaps the most popular invertible neural network. Real NVP is perhaps the most popular flow-based model. And in fact, in last time when I taught uh, flow-based model or normalizing flow in probabilistic machine learning, the actual course, right? I mean, not actual, I mean the basic one. So there actually I only covered real NVP. I did not cover this variance. Now I'm covering this variance because it's a course on deep generative model. So I should go into more depth and more variance. Okay. So in real NVP, right, you have just one image. We have not one image, let's say one vector. Maybe I should write what should we suppose we have one vector. Let's call it x. How will I use real NVP in this case? Right? Because in real NVP, the whole transformation is based on x1 and x2. Right? x1 is equal to x1 prime is equal to x1 x1, x2 prime is equal to x2 plus m theta or exponential of s times x2 plus whatever. We know that, right? But in reality, I will not have x1 and x2. I will have only one. So how do I use it? There are two ways of doing that. Two ways. The first one is you take a vector and randomly partition it. Partition it. Okay. So you have a vector, you take it and randomly partition it into two parts. And then one part you will be x1, other part will be x2. I mean the easiest possible solution you can think of, right? So this is one way. This is perhaps the more popular way. So you just break it and break the vector randomly and break it every time. Don't keep the same division. If first, suppose it is 1, 2, 3, 4. First time you are taking 1, 3 and 2, 4. Next time you can take 1, 4, 2, 3 or so. Change it, randomly sample it every time. Because remember that one portion will not change. x1 prime will remain equal to x1. But ultimately you will want everything to change. So that's why you don't keep the constant part same, because then you are not getting expressive enough things. Yes. So in the real NVP, what is the transformation? x1 prime is equal to x1, x2 prime is equal to exponential of s multiplied by x2 plus m of x1, right? So focus on x1 prime. x1 prime is equal to x1. That means there is no change in that part. Correct? Now how am I getting x1? By splitting x into x1 and x2. If I keep this x1 part constant, if I keep it constant, then what will happen? One portion of the image will remain to be noise. There is no transformation happening in one part. Other part, all the things are happening. It's not a good idea, right? Yes, if you do that, then it's fine. But people, what they do, they don't do that alternatively. They just do it randomly here. So that solves that problem because you anyways have multiple of those layers, fine coupling layers, right? So because of that, it will, if you sample it randomly, that's okay. Clear? Yes. During the training. So it becomes a step actually, which is x1, which is x2, you keep on changing that. Okay. That also people do, but if you, because you can do it by, so it's same thing, right? In BAE, all the derivations we did was based on probabilistic, right? But in practice, you draw one sample. Same thing. When you do that, that should be done, but then that becomes expensive. What people do is, instead of doing that, I will do it randomly here and do it less number of time, and that will probably converge. So that is the idea. You don't have same parameter. That m theta. So let me draw it here, right? This is a good time to draw it. So you will have something like this, right? This is what you will have. Each of these can be a affine coupling block, and each will have its own parameter. And you need to train all those parameters. So the parameters are not shared. Right? That's what I was saying, that union of thetas is actually, unions of theta i's is actually theta. Okay, so they are not shared. Okay, this is one way of doing it. There is one more reason of partitioning it randomly, because you don't want a pattern to emerge. I mean, you want it to be random, right? So that there is another way of doing it, which is actually will give the same result, but there what you do is that you multiply this x. So this is option 1, right? Option 2. Option 2, you have x. You multiply by S, which is a random projection matrix. And so you multiply it with x. Okay. And now you partition it, and now you can partition them deterministically. Does not matter. But this matrix should change every time. That should remain random. It's not a single random, it's a random. Basically, we understand you will get the same thing. So here what you do is you multiply with a random matrix, you project it, and then in the projected space you kind of take 1, 3, 5, 2, 4, 6, something like that. Or 1, 2, 3, 4, 5, 6 is also fine. This is easy than the previous one for implementation. Because instead of drawing random integer and then collecting them, that is expensive. Here you just generate a random matrix, multiply it, and then just slice it. Why are you not? Here we are doing randomly. Ultimately, x1 and x2 should not remain same. I want them to be random. I can make them random in two ways. One is the data you select randomly. Some will go to x1, some will go to x2 randomly. That is what we are doing here. Second one, we are randomly projecting it, so the projection itself becomes random. And now you are doing it deterministically, so then it changes. Right? Your vector, right? Input has a vector. It has to be same. The dimension should not reduce. So it's a square matrix. So if that is k, this is k cross k. So you will get k cross 1. Not exactly permutation, random, right? So it need not be permutation. I mean, so it should not be obviously rotation tensor, so that it becomes. Yeah, sorry, go ahead. No. It is not random. It is random and known to you, known random, something like that, right? It's not trainable. Because if it's trainable, then it will learn a pattern, and you don't want that, right? So this is how you split it. Same thing you can do for image. You can imagine that if you have an image, you split it into 4 parts, 2 part, 3 part, 4 part, and all of those things. Okay. For image also same thing will hold. I'm not telling anything separately for image. How the splitting is done is also interesting thing. So there is a model known as GLOW model. GLOW is a type of flow model. But the glow has a very specific kind of splitting where you split the image into some deterministic way and then do some overlapping kind of thing. So glow is another of flow based model. So there are, again, these are families of model you should keep in mind. What I am trying to cover in the lecture is the fundamentals that can allow you to now do many things on top of that. Because what is the fundamental of flow based model? It is the transformation distribution, it is the invertible mapping, and it is that it should be easy to compute. So you can go ahead and design your own invertible layer. Like you were suggesting, why not X cube? I said it is easy, not easy. I said it is may not be expressive enough, right? But that does not mean you cannot use it. For certain class of problem, you can use X cube, and that, for that problem, it might be very good, and that might be the best invertible model for that problem. But that might not generalize to all problems. But that does not mean you should not use it for that problem if you know that property. So the foundation is that. Based on that foundation, whatever you want to build, you build. And that is the whole idea of the project. If you want to build a invertible model of your own, you go ahead and build on top of this. You know the foundation. Now on top of that, you can find your own invertible mapping. You can do some Fourier and inverse Fourier, and that might be a invertible. And Fourier and inverse Fourier is obviously invertible, but with the nonlinearity, you can probably do something. I don't know, right? Like that sigma plus whatever I'm doing, that you can have some Fourier and inverse Fourier transform there sitting, and maybe that will improve. There can be some wavelet, there can be some Laplace. So you can come up with your own invertible mapping in this case. For VAE, you know the foundation that Z given X is best. One of the things that combining flow with VAE that people have already done, but you can come up with your own ideas that how I can approach that Z given X as the optimal one, so that my training becomes more robust, better, accurate, whatever is the correct terminology you can select for yourself, but that is the idea. Autoregressive, you know, right? Autoregressive people are using transformer, you know that. But now suppose some of you are working on scientific machine learning. I mean, you can always come up with an autoregressive generative model where the autoregression is not with transformer, but let's say with DeepNet. Let's say is with FNO. Those options are open. You know what is autoregressive model, but what are the different possibilities of autoregressive model is up to your imagination. There is no limit to that. I will obviously not cover everything. But my objective is to cover the fundamental to the best of my ability. Okay. So tomorrow there will be a lecture, same time here. We'll start and finish GAN. That is my objective. And day after tomorrow, the exam. I said everyone got that email, right? I mean those who are registered, obviously. 8:30 is what I said. I'll book the room. Not here, maybe there. I'll see what room is available and let you know. Syllabus is whatever I cover until tomorrow. Okay. Okay. So syllabus is whatever I cover until tomorrow. Okay. Thank you.